This is 2018 AIME I problem number 13, and here is a view of this problem as well as a simple sketch right underneath the problem. We're given a triangle ABC with the following side lengths of 30, 32 and 34. The point X is a variable point between the vertices B and C alongside the edge BC of our triangle. Next, we draw the incenters I1 and I2 of the triangles ABX and ACX respectively. And finally, we would like to find the minimum possible area of this green triangle AI1, I2. A very similar problem appeared on the 2009, I believe AIME II, but it might be AIME I as well, so please check, as a number 15, problem number 15, almost the same type of construction, except that in that problem we were drawing the circumcircle of BI1X and CI2X, and we let those two circles intersect at a second point besides X at P, and the question was asking another optimization problem where the question was asking for the maximum possible area of triangle BPX. So along the same spirit here, so we have these two incircles suggesting that these angles are equivalent, right? They are congruent angles. Those two angles are congruent, and then these two angles are congruent, as you can see here on my marking. And it suggests further that this angle here is just half of angle A, right? For instance, if you have these two as alpha each and those two as beta, so angle A would be 2 alpha plus 2 beta, and this angle in the middle would be alpha plus beta, or if you will, let's just write it as angle A over 2. So that would suggest that we can calculate the area of this triangle. Let's write that down, AI1, I2, simply as 1/2 AI1 times AI2 times the sine of the angle between those two sides, which is just angle A over 2. And that's it. That's exactly what we want to minimize. It turns out that, as you can clearly see here, this one is just fixed. It's given the problem, the side lengths are given, suggesting that the angles are fixed as well. So this portion is fixed. So when you try to minimize this, what really you are doing is, because this number is fixed, that one is fixed, all you are doing is minimizing this product here, and this is exactly what we will be focusing on next. So my solution will be following djmathman's solution. I believe that problem also belongs to him. Very nice problem. His solution is pretty nice. Towards the end, he does a really simple mistake, but that's okay. So we will mention that quickly. And so let's go ahead and attempt this problem now. Because I1 is the incenter of triangle BAX, I can just draw this line here. So we have these two angles. They both measure B over 2. And I can similarly connect these two here. And this one is C over 2, that one is C over 2. Next, because the point X is a variable point between B and C, we will eventually calculate the area of this green triangle in terms of something that relates to the point X. So one idea is to consider this angle over here. Okay, so we will try to make our expressions in terms of this angle theta here. So one quick angle chasing argument would show us that this angle here is indeed 90 plus theta over 2. This is one of the angles that might be useful to memorize actually, and from there we can try to get an expression in terms of AI1 simply by focusing on triangle ABI1 and applying law of sine on triangle ABI1. So let's go ahead and mention that. On triangle ABI1, and from there we would get for instance AI1 to angle B over 2, sine of angle, well, or you can just say b over 2, I guess. B over 2 is equal to opposite AI1 is b over 2. Let's say opposite this angle here is just AB, which we already know measures 30, right? So AB measures 30 divided by sine of angle 90 degrees plus theta over 2. But then it's clear that sine 90 plus theta over 2, if you use the addition formula, for instance, sine 90 times cosine theta over 2, which is just cosine theta over 2, minus cosine 90, which is 0, so I don't have to worry about that part. So that whole thing is just cosine of theta over 2 here. Well, there's a 30 here. Okay, so that's kind of the first part. Hold on. Yes, is AB? Yes, it is 30. All right, in the second part, I'll pretty much carry the same analysis to this one, to triangle AI2C now. I need to measure this angle. Well, because this angle is 180 minus theta, I will apply the same rule here. That one would be 90 plus 180 minus theta all divided by 2. So 90 plus 90 is just 180 minus theta over 2. So then finally, apply also, we're applying law of sine on this time triangle ACI2. We would get AI2 divided by AI2, opposite is sine C over 2. C over 2 is simply equal to the length opposite, this is AC, which is 34, divided by sine of angle, that thingy here. I hope I didn't do any silly mistake here. So 180 minus theta over 2. And obviously 180 sine 180 minus theta over 2 is just sine theta over 2, right? And so that one is a 34. And now we can just cross multiply these and we would get the two expressions for AI1 and AI2, and that's exactly what we need, to be honest. So let's go ahead and plug them into our formula here. So therefore the area right before the optimization, the area here is equal to 1/2. AI1 is just 30 times sine of angle B over 2 divided by cosine theta over 2 times 34. Maybe yeah, let's just keep it like this, 30, and then I have a 34 here. The same thing, sine C over 2 divided by sine of theta over 2. What we can do is we can treat, knowing the double angle formula, the denominators, have a look at these. 2 cosine theta over 2, sine theta over 2. This is just sine theta, right? So this is double angle formula for sine theta. So this is just sine theta in the denominator. And in the numerator, we have 30 times 34. Oh, wait, I'm still missing this one. I was just thinking, hey, am I missing something here? Yes. So we have sine of angle A over 2 is missing. Because it didn't look for a minute like it was symmetrical after all, so that raised the flag. So 30, 34, okay, so I'm missing, oops, let's fix the color. Sine B over 2, sine C over 2, sine A over 2. So that is just a very impressive expression. So sine A over 2, sine of B over 2, and sine of C over 2, and that's it. So now the main challenge is to establish what these 3 and 3's are. Well, the reason I say that is because remember that we are trying to minimize this expression. Obviously, because sine theta, sine is always between -1 and 1, right? And obviously we are in the positive range because our theta cannot be more than 180, so therefore it's really between 0 and 1. So if I remove it altogether, my whole fraction will be will get smaller. Yes, because with the existence of sine theta we are bigger. Yes, so that's just 30 times 34. and then just the remaining part, sine A over 2 times sine B over 2 times sine C over 2. That's it. So therefore, knowing now that the minimum that our expression can attain, the minimum it can attain with an equality condition here is when so when sine theta here is indeed equal to 1, right? So that's when sine theta is equal to 1, suggesting that theta itself is 90 degrees, right? So basically the location of x is really the foot of the perpendicular or the altitude, right? So this is when you get an optimization. You can call it as x star if you will. Does that make sense? But then going back to our expression, now that's the minimum possible value of for this given area, this given green triangle. And so the important part now is just to obtain this product, sine A over 2 times sine B over 2 times sine C over 2, and it's just a matter of time to get to that. So we can do it independently. So let's go ahead and do that. Probably different color. So let's use the double angle formula. So for instance, cosine of say A over 2. Well, okay, so cosine A, let's say. So cosine A, think of it as a double angle, right? So cosine A is just 2 cosine square A over 2 minus 1, or 1 minus, okay, so this one is important, 1 minus 2 sine square A over 2. And from there, it's possible to get an expression for sine A over 2, obviously. Just replace these two expressions. So we would have 2 times sine square A over 2 is simply equal to 1 minus, not plus, minus cosine of A. We can divide both sides by 2. Dividing both sides by 2, I would, okay, and finally take the square root, basically. That's it. So sine A over 2 is equal to square root 1 minus cosine A all divided by 2. So there's just a minor error here on AOPS forum page on djmathman's solution. Otherwise, his solution is just perfect, and all this solution is based on his, actually. And finally, we can just find corresponding expressions for sine B over 2 and sine C over 2 as well, no doubt. So therefore, it's a good idea that we just multiply these expressions now, right? So when you multiply these expressions, well, actually, right before you multiply, we can be smart and we can replace cosine A with what we get from law of cosine. So from law of cosine on, say, triangle ABC, and in particular, because we need cosine of A, we get A square equals B square plus C square minus 2BC cosine of angle A. And from there, it's obvious that cosine A is simply equal to B square plus C square minus A square all divided by 2BC. Now we can go ahead and substitute that into our expression. So therefore, sine of angle A over 2 would simply be, let's rewrite this nicely. Sine A over 2 would simply be equal to square root of, okay, so this is an ugly expression here. 1/2 1 minus, okay, so cosine A is just this monster, B square plus C square minus A square all divided by 2BC. We can find the common denominator of 4BC, square root BC, and we can factor out the 4 if we will, or we can just keep it, and eventually it will, when we multiply them out, it will all vanish. So we have square root of, so we have 1 over 4BC, and having the common denominator here, we will have 2BC minus B square minus C square plus A square, and this can be finally written as 4BC. Okay, so the inside would be A square. In order to get A square, I will have, so I think I should have A plus B plus C, and then A minus B. Oh, no, this one is a minus, sorry. Okay, yes, that's a minus, this one is a minus, this one is a plus. And simply using a similar strategy, you can easily find sine b over 2 as well, and just purely exploiting the symmetry we got here, that would be 1 over 4 AC apparently. And then so look at how A is positive here, and then the B and the C alternate. So it would be the B positive here, A and C will alternate. So minus A plus B plus C times A plus B minus C. And finally, sine C over 2 would simply be equal to square root of 1 over 4AB, and then we would have, this time the C will not alternate, so minus A plus B plus C, and A minus B plus C. Now it's I think quite clear how you can simply multiply these three, and so that you can just substitute into this expression. So when you multiply all these expressions, we have 4 times 4 times 4, 64, square root is just 8. Then we have A here, another A squared, so we have B squared, and then we have a C squared. So ultimately when we multiply these three, we will get therefore sine A over 2 times sine B over 2 times sine of angle C over 2 is simply equal to 8 and 1 over 8 ABC. And then look at the expressions. These are, well, these 6 expressions, all these products. I think one can recognize that some of them are the same. For instance, we have here and here the same expression, so they will come out of the square root. So therefore I have minus A plus B plus C. Similarly, A plus B minus C here, A plus B minus C here, that's out. A plus B minus C, and the other expressions are the same as well. A minus B plus C. All right, so but this is decidedly a known quantity, right? So it turns out that A, B, C are just going back to the beginning of the problem. They were 30, 32, and 34. So that's quite easy to handle. And then recall that, okay, so we are plugging into this expression because we are minimizing that. So therefore the minimum, so the minimum area of A, I1, I2, I would have named them I sub A, I sub B to be honest, but that's all, that's okay. So 1 over 8 times 30, 32, and 34 times this whole thing. Oh, I shouldn't forget about adding these 30 and 34 as well. Let's go ahead and add those two too. So 30 times 34. And now it's time to just plug in these values all into this expression. Let's just remember which one is what. So that's a C, that's an A, and this is the B. So 32, 34, and 30. So 32, 34, and 30. 32. All I do is make sure the signs are correct, otherwise the rest should be pretty straightforward. And that's it. The 30s cancel out, the 34s cancel out, so I have 1 over 8 times 32, and so the first parenthesis will give me 32, the second one would give me 4 plus, so it's a 36, and finally the last one minus 2, 28. And that's it. So the 32s cancel out, the 8 and the 36, there's a 9 here, a 2 here, the 2 and the 28, there's a 14 left here, and indeed 14 times 10 is 140 minus 14 is 126 is the answer to this beautiful problem. One of the other solutions that impressed me on AOPS forums were from a user named Canton Matt, and his idea was pretty cool too. So what he did is he extended this line BI1 and CI2, and he just observed that because of the homotety, oops, I don't think this is straight line, because of the homotety involved between the incenter of triangle ABC and these two incenter of ABX, for instance, these two are, so BI1I is collinear, CI2I are also collinear, and then you can extend the angle bisector AI1 using the usual formulas, you can calculate AI1, which shouldn't be too hard, and then from there you can find the ratio BI1 to II1, similarly CI2 to II2. What impressed me the most is that the product of these two ratios are just happens to be 3 for this particular triangle with side lengths 30, 32 and 34. So therefore it's kind of a very nice type of argument, and then there's still an optimization going on, and I highly recommend you guys read that solution as well. But this is a standard computational geometry problem. In essence, it's the picture is relatively the same to this one, to the picture here, where the setup is the same. The only thing is the question we are asking a different optimizing a different piece of area. But pretty nice question. Hope you enjoyed this solution, and looking forward to see you guys in our next lecture.